cool, like little smoke plume as it escapes.
Troll! There's a troll in the dungeon! There's a troll! There's a goddamn troll in the dungeon! Oh my god, there's a troll! I just thought you want to know.
Whoa. I don't know what's going on when I show the portraits.
I'm gonna leave on that one.
It's too bad about the troll. Awesome. Sometimes I found something in my dungeon. Probably what to do. I don't know what's wrong with this. I'm not that savvy. I'm only on book 8 of Harry Potter. Is there a troll in Harry Potter's dungeon? Cool. That's awesome. Harry Potter's a little scandalous. Like, I could never invite anybody to my chamber of secrets. You know what I mean? I'd never. But somehow he gets away with it. He got a big movie of it. Okay. Let's try this problem since we're thinking about stuff. I'm all excited. This is probably the best class I've ever been in. Okay. First it was the banana. I think it was the banana. Okay. Ammonia gas. We'll see. Maybe I should bring stuff to protect myself. So, ammonia gas, occupying volume of 3.5 liters at 1.68 atmospheres is compressed. Okay, so we see a volume change and a pressure change. Automatically, we know we're in one side of the solving method. What I would do is write down the combined gas law. Okay, and just see, okay, there's a couple things that don't change. Let me cross those out. I know pressure and volume change, so I'm going to knock out those. The moles and the temperature, because they're constant, they're not changing. Notice the moles aren't mentioned specifically, but it says nothing about them changing. Okay, it looks like this is a set container that's not letting anything in or out. Okay. So I want to know the final pressure, so let me just circle that. We're finding this one right here, P2. Okay? And so if you want, you can make a little table while you're getting used to how to think about this. And you could say, well, N and T over state 1 and 2 don't change, but the volume goes from 3.5 liters to 1.35 liters. And the pressure goes from 1.68 atmospheres to, we don't know, so I'll say P2. And so you just plug this in. P1, 1.68, times 3.5 equals P2 times 1.35. Now, do I need to worry about the units? Do they need to be in SI units? Is what I'm concerned about. No, not in a comparison problem when there's two states. Just like Graham's law, or just like the dilution calculation, as long as you're consistent, meaning your volume units must be the same, liters here, and your pressure units must be the same, atmospheres here. As long as that's fine, you're doing this initial to final state calculation, it really doesn't matter. So these kind of gas laws, when there's initial to final state, including Graham's law, and even including a chapter 4 dilution law, you don't need to worry about the units. In general though, we use SI units, is what I'd recommend. Okay, outside of also the ideal gas law. So hopefully you get those units kind of straight in your mind. Do we expect the pressure to go up or down? The volume decreased. If you're pushing on the volume, you'd expect a higher pressure. You're pushing in on the volume, expect a higher pressure. That's exactly what happens. We get P2 equal to 2 sig figs, it looks like 4.4 atmospheres. Okay. This is a pretty typical, I consider like easy to medium level kind of question. Okay, I have another one up as well. This one. Okay, honestly, I don't ask these weird students to come and run over the class if you're wondering. They just do it for fun, but I do think it's pretty fun. Okay, so let's try the second one here. There's actually a couple ways to solve this problem. So I'm going to use, you'll see 2 methods to solve this problem. First let's write down the reaction, see what we have going on here. We have HCl plus Na2S was collected, and it's produced by a reaction. So the foul smelling gas was collected, produced by this reaction, okay? So we want to know the molecular mass of the gas, likely formula name, etc. In fact, I think there's 3 ways to do this problem. So way number 1, this is the there's an easy, a medium, and a hard way to do it. We're going to do the medium way first. Method of solving number 1. You could say, hey, it's an STP. I know a conversion factor STP. Let me use that. So I have 1 liter that I start off with. I need to find moles. I can say there's 1 mole for every 22.7 liters, and that gets me 1 over 22.7 moles, or 0.04405 moles. Okay, so there's both moles. And because I know there's 1 liter collected, this is the moles of the gas. I need to know the molecular mass of the gas. Let me write that out. So the molar mass or molecular mass is mass over moles. Okay? I know moles, and mass is given, 1.52. So you go 1.52 grams, given in the question, divided by what I just found. And this turns out to be 34.5 grams per mole. There we go. So there's 1 way to solve the problem. Let's look at a different way to solve this problem. Way number 2. This one's a little bit harder, just because it takes more work, but conceptually it's the same. You can find moles using the ideal gas law. Why might you think of the ideal gas law? Because there is a reaction, but there's really no change in moles or volume or pressure or anything like that. So you think, okay, ideal gas law. Let's try that. So you go 1 bar, and let me do the denominator real quick here. 0.08206, this is the one I told you to use for the ideal gas law. This R per mole Kelvin times the temperature is 273 K. Yeah, because it's standard temperature. Okay? 1 bar because it's standard pressure. Now my units need to match R. It's atmospheres in R, so I need to change bars to atmosphere. Here's the conversion. 1 atmosphere is 1.01325 bar. So there's the conversion that would be given on the exam. So you know that. Okay, next. Volume given in the problem 1 liter. So we're just using the givens in the problem. P and T from an STP, standard temperature and pressure. Volume's given, R is a constant. What do you get? Oh my goodness, you get the same thing. Who knew? 4405 moles, just like up above. And then from there, the solving method would be identical to method 1. So you'd use this calculation here as you did up above to find the molar mass. Okay? So it's just a little more involved mathematically because you got this big equation to deal with versus a straight up conversion. Both methods totally reasonable. Now let's do method 3. What's another way we can solve this? You could have just said from what, chapter 4? What kind of reaction is this? It's a double replacement. So we were going to get 2 sodium chlorides. There'll be a 2 here plus H2S. You know sodium chloride isn't a nasty smelling gas because it's table salt, so it's H2S. What's the molar mass of this? About 34.5. So that would be method 3, probably the easiest. All of those are totally fine methods to figure out what is the molar mass of the gas and what is the gas. Okay? Any questions on that? This was ultimately to illustrate the second one, but I also wanted to show you methods 1 and 3 are all fine. And I'll toss this. Oh my goodness. Lost power. It'll come back in a moment. I put up YouTube. There's ideal gas law 1, 2, 3, 4, and 5. If you want to see more examples. They vary from medium to difficult. One of them, I think the ideal gas law 3 is a difficult question that you'll see on the homework. Okay? That you see on the online homework. So if you get stumped by ideal gas law question or a question you don't get how to do, take a look at ideal gas law video 3. That's solving one of the questions from the homework. Okay. Section 5 now. Another law, there's a bunch of them. Law of combining volumes. Law of combining volumes. This law says that it's kind of like the law of multiple proportions. It says that gases combine, so it's talking about reactions. Gases and reactions combine in small whole number ratios. That's the law of combined volumes. Gases combine small whole number ratios. What that does, and I'll show you something that's in the reader. This is page 51 of the reader. This table. By the way, in the textbook, section 5, let's see where that is, just so you follow along section 5. That's page 212 in the text. In the reader, we're on page 51. Okay, I have this reaction, N2, you've seen it before, this is the Haber process. N2 plus 3H2 goes to NH3. We saw part of this table before on the microscopic scale that we're not really using in class. 1 molecule of N2 goes plus 3 molecules of H2 go to 2 molecules of NH3. Okay? But we're thinking more on the macroscopic scale. So far, we've thought of the coefficients as moles. 1 mole of N2 plus 3 moles of H2 go to 2 moles of NH3. According to the law of combining volumes, you can actually think of it as liters, if they're ideal gases. So 1 liter of N2, 3 liters of H2 form 2 liters of NH3. So there's now, in addition to mole ratios, there's now volume ratios. Okay, so we get these volume ratios that are just like mole ratios, but they involve liters. You can actually derive the law of combined volumes, or demonstrate it at least, by taking this formula and multiplying through by that STP conversion, 1 mole for every 22.7 liters. You cancel out the moles and you get liters, and the 22.7 will also drop out on both sides, and thus you're left with liters. So you can also demonstrate it. We won't do it in class, but it's pretty simple to do so. Okay, so that's that. What does that lead us to here? We're going to get another molar express. Now, remember, we used to have only one way to get from one molecule in reaction to another, and that's a molar ratio. Now we can take a volume ratio. There's a second pathway to go from one compound to the other. By the way, this is also posted on Smart Site. It's in the reader. So you can go from volume to volume way up there at the top via the volume ratio. Okay? So sometimes if you have ideal gases and if you are at or near STP, the volume ratio is a pretty convenient calculation. You can use it again with ideal gases at or near STP. And it should work fine. And there's a lot of examples on YouTube. You'll see the law of combining volumes. There's a limiting reactant problem you can do with gases now. Yes, it carries over. And there's gas stoichiometry problems, all kinds of fun joys on YouTube that you'll see listed on the bottom of page 51. I think I have just one simple example for you, so you can, just so you can visually see how this works. If you take that reaction I had before, and let's just say you have 5.55 liters of N2, and you wanted to find the volume of ammonia, you just say, well, there's 2 liters of ammonia for every 1 liter of N2. So this is a volume ratio. The liters cancel, just like a molar ratio would work. You'll get 11.1 liters of NH3. So really simple calculation, as opposed to, if you don't do it this way, your only other option is to convert, use the ideal gas law or something like this to go to moles, use a molar ratio to get to NH3, and then use the ideal gas law again to go from moles of NH3 back up to volume. So it involves several more steps mathematically, and just a little bit more painful. So just to know, this is a really nice shortcut. Section 6. And I hope you all are doing practice problems of this. When you get home and stuff, so you get used to how to do stuff. We're on page now, though, 52. In the textbook, this is page 214. Another law. Of course, we like laws. So the next law is called Dalton's Law. We'll slow down on this one a little bit. It's Dalton's Law of partial pressures. And this occurs or needs to come up whenever we have a mixture of gases. So up to this point, we've only been talking about one gas at a time. Now, and sometimes that gas might change state, but it stays the same gas. In this case, we've got more than one gas in the system at the same time. So a mixture of gases. Usually we're going to talk about 2, but it could be more than 2. And here's a couple things that we can learn about these gases. And let's say you have a container, and in the container there's gas A, there's gas B, there might even be gas C, all kinds of gases in your container. You would say that the total pressure in that container is equal to the pressure exerted by A, plus the pressure exerted by B, plus anything else that you got in there, pressure exerted by C, etc. These pressures here on the right-hand side are specifically called partial pressures that each contribute to a total pressure. So specifically, it's the partial pressure of A, the partial pressure of B, etc. So the sum of the partial pressures equal the total pressure. You can also say this you probably knew from before, hopefully. The moles of A in the container plus the moles of B plus any other moles of any other component will equal the total moles. So the sum of all the moles equal the total moles. That hopefully you knew from, say, the law of conservation of mass or intuition. And we can also say something about the volume. The volume occupied is equal to the volume occupied by A plus the volume occupied by B plus any other compound in the system, in the bottle. So there's something else we can do with this. We can define something XA which is called the mole fraction, in this case of A, mole fraction of A, or lowercase x of A, and this equals, as you might guess, the moles of A over the total moles. Hopefully that kind of makes sense. The mole fraction, or the fraction of moles, is the moles of A in the container divided by the total moles of the container. But what's interesting now with this is we can do something else. We can say, hey, that's also the partial pressure of A divided by the total pressure. And now we're getting into Dalton's Law. And just one more I'll toss in there if you ever see it. It's also actually equal to the volume of A over the total volume. But if we take, and I'll change pen colors now, this part right here, this is going to make up what we traditionally call Dalton's Law, which you solve for usually the partial pressure. So you'd say the partial pressure of A is equal to the moles of A over the total moles and total times P total. Or you could say partial pressure of A equals the mole fraction of A times P total. Either way you write it, this is Dalton's Law. Dalton's Law. And you'll see these formulas also kind of elaborated in the text. Now, let me add to this on the right-hand side. This makes the ideal gas law kind of interesting at this point. So what you can say about the ideal gas law, leave a little space here between the letters. You could say that P total times V total, as we saw above, equals N total RT, just to make the ideal gas law a little more specific. But, and we're not going to go through any of these derivations, you could also say this: PA, the partial pressure of A times V total, equals the moles of A RT, or, to kind of flip it around a little bit different, P total equals the volume of A N of A RT. Now all those work, but in our class we're going to tend to use these top two the most, because we'll usually care about the partial pressure and the specific moles, say, of A. But all those would hold. Okay, let's write down this question. See how Dalton's Law works out? In this case, in scuba diving, you are a scuba diver. Dalton's Law is pretty significant. You need to get the right pressure in the tank so you don't get the bends, and dilute it appropriately to exactly the pressures that you need. Okay? So next time you go scuba diving, take your calculator, your pencil, so you can figure out what exactly you need. By the way, while you're writing that down, February 10th, which I think is Monday, yes, at night in 7 p.m., Chem 194, I'm doing this thing called the last lecture. I don't know if you've heard about it in the media, but ASCCD picked this up. It's supposed to be the last lecture right before you die, what you would say. I don't think I'm dying, but maybe ASCCD thinks I'm dying. And I'm going to give my last lecture apparently, but hopefully I will be on class on Tuesday as well. But last lecture series thing that they do for faculty, it's in Chem 179 right behind me at 7 p.m. Okay, let's do this problem. Apparently it's on Facebook too. I think I said I was going. All right. Let's try this problem here. There are different ways to do this problem, in fact. So I just want to alert you to that ahead of time. There's multiple ways to do the problem, and maybe I'll show you this first, just so you can see my way before I do it. So I'm going to move this for a moment. Let me show you this first. How do I solve the Dalton Law problem? This is also in a different form in the reader if you want to look there. Now again, there's many ways to solve the Dalton Law problem. As long as you're using appropriate chemical techniques that don't violate any laws, I'm totally fine with that. You take your given units. Usually it's mass, or they'll give you like pressure, volume, temperature. Take those units, whatever they are, and convert to moles. How do I do that? I use the ideal gas law. So I convert to moles using the ideal gas law, depending on what they give me. But if it's just mass, you can just do use the molar mass to get moles. So either the ideal gas law or using the molar mass. And then what I do, what turns out to be convenient for me at that point, once I found moles of every component in the system, I want to add them together to get the total moles. Okay? And this is just, I'm trying to elaborate every single step. Sometimes you can do multiple things at the same time depending on what they give you. But if you're going through every single step, this is what I do. So the fourth step is I find the mole fraction. So you got the total moles from adding up all the moles, then you find the mole fractions. So that's the X sub A. And if you do being exhaustive for every component, but really for the component you're most interested in is where you want to go. And then after you find the mole fraction, typically what they're going to ask you for in a question is one of two things. The total pressure and or the partial pressures. So those are typically what Dalton's Law question would ask for. If you're asked for the total pressure, I would use the ideal gas law, but the total version of it. P total, V total equals N total RT. However, sometimes you're just given the total pressure, which is fine, and they ask you for the partial pressure. Whether you're given the total pressure you have to calculate, it doesn't matter. You can still find the partial pressure. How do you find the partial pressure? You just use Dalton's Law. So use Dalton's Law, you know the mole fraction, you know the total pressure at this point, just calculate the partial pressure. So that's a solving technique that I use. You don't have to go through the ideal gas law. Some people use one of the gas laws where there's change. So for example, Boyle's law or something like that. That's totally fine too if you want to do it that way. It's just my method. Okay? Right, so that's my typical Dalton's Law method of solving. That's what I'm going to impose and use right here. So what you're going to see, for the first step, I need to find the moles of both compounds in the gas. Say, in that case, that's helium and oxygen. But what I just noticed, it's 10:17 and you might be tired. There's no way I'm going to finish this problem. Is it okay if we do it next time? Yeah. Cool. Take care. Have a good weekend.